All right, hey everyone. Welcome, thanks for coming to this AI for Climate Change Symposium. I'm grateful also to my co-organizers, Jeremy and Sharon, for helping put this together. I'm excited to be here today because I hope this will be the first of maybe many things we'll do here at Stanford to use AI, machine learning, deep learning, to make a big difference to what may be the biggest problem, certainly one of the biggest problems facing humanity. And so I hope that many years from now, each one of you will be able to look back and say, yep, that date, April 7th, 2019, it's April 7th, right? I was there when this thing started in Bishop Auditorium. A lot of climate change feels very far away, right? Like when you read in the news, you see, gee, by maybe 2050, this will happen by the end of the century, by 2100, maybe sea levels will have risen by 3 feet or 6 feet or 7 feet or more. But I think people alive today, including many of us will be affected by these changes. Some of you know that I just had a daughter, my first daughter 2 months ago, and the children of today will come of age in an era shaped by the decisions we make today. And so when I read of the changes that the world may face by the year 2100, I don't know if I will experience them myself, but there's a very good chance that our children today will. And it is up to us to make sure that just as we inherited this wonderful planet from our ancestors, that we build it in a way that we could leave it to ourselves, our older selves will still be alive for many decades, but also to our descendants. And of course, climate change isn't just about what will happen in the years 2050 or the years 2100 or beyond. And some projections are that things will get even worse beyond 2100. Arguably, some of its impacts are already on us today. Right here in California, many of us living in Stanford, living in Palo Alto, experience secondhand the impacts of the recent California wildfires, where the air here was a dark gray, was gray, and we were breathing that air every day. But of course, what we experienced up here in Stanford was nothing like what people experienced at ground zero. A campfire was the single most deadliest and most destructive. Oh, what are you guys doing? All right. Oh, speakers. So campfire was the single deadliest and most destructive fire ever in history in California. About almost 20,000 structures were destroyed, and it created $16.5 billion worth of damage. And apart from the financial damage, there was countless lives uprooted, disrupted. And while we can't prove that climate change causes, we believe that hotter temperatures as well as drier forests was a major contributing factor, causing wildfires to be perhaps deadlier and more destructive than before. So we have fire. We also have water. And again, just last year in the Carolinas, Hurricane Florence caused 60 deaths and about $24 billion worth of damage. And while, again, we can't prove that climate change causes, and climate change probably did not cause this, warmer temperatures, more evaporation of water, we believe is on average making storms worse. So World Bank recently had referred to a paper which cited that by 2050, without concrete climate and development actions, just over 143 million people could be forced to move from their homes. And this is a study not of the whole world, just on parts of the world that comprises 55% of the world's population. So the actual number of people that are forced to move may well end up even larger than this. And so the actions that we take today will affect whether or how many of these millions or tens of millions or hundreds of millions of climate refugees there will be in the future. There's a recent paper from Cornell that estimated north of 1 billion climate refugees, which is a less widely accepted result, but the estimates for how bad things could be based on rising sea levels. And I think today, rising sea levels of maybe 3 feet by the end of the century seems plausible, and possibly 6 feet, maybe 7 feet, maybe even more, and the climate models do not give us a lot of certainty, but there will be great harm and potentially much greater than we're even estimating today. So what can we do? Why AI and climate change? Here in Stanford, certainly in the AI community, we're privileged to have access to amazing algorithms, amazing breakthrough technologies that did not exist 2 or 3 years ago. And AI gives us a new set of superpowers. AI, or machine learning or deep learning, is also not panacea. So can it actually make a difference in climate change? Here are some of the things I think the Stanford community, including the AI community, but more broadly, can step into. Today, we do not really understand how Earth as a physical system works. And even though we have coarse models of how the Earth works, for example, we run simulations where the discretized cells, maybe 500 kilometers by 500 kilometers, maybe down to 100 by 100 kilometers. We run very, very coarse simulations of the planet Earth. And there's a lot of data out there, right? Maybe hundreds of terabytes of data per day being collected by satellite imagery, distributed sensors, many, many sensors. And the number of people working on this data seems extremely small relative to the importance of the problem and the amount of data out there. You know, I've been maybe privileged to have seen a lot of the work, to have seen some of the work that Silicon Valley, the AI community, has put into getting people to click more on ads. And this turns out to be incredibly lucrative, and the investment in that one problem is massive. If we have 1/10 as much work on climate change as we have on getting people to click on ads, I think we can make a big difference to this problem. Again, hey, getting people to click on ads is not a bad thing, nothing against it, but I think we should do this too. And maybe just some specific examples. WCRP, the World Climate Research Program, lists a number of grand challenges on climate modeling. And for example, first one, melting ice and global consequences. I think we do not understand what are the impacts of melting ice in the glaciers. We do not understand when permafrost melts, how much does that release additional methane, how much does that release additional carbon dioxide, and what are the closed feedback loop systems. And there is data that needs us to work on, and many other modeling problems besides. I'll just mention one class of problems that I think is important. One class of really research problems that I think is very important for climate science, but also for machine learning more broadly, which is that climate science is fundamentally about simulating a physics-based system, and we do have physics-based simulators. One technical problem that I see in many disciplines, not just in climate, is if you have a physics simulator that's pretty good, but not perfect because you can't simulate to the very fine grains, but you also have data. If you don't have enough data to use a pure machine learning approach to say, oh, discard the physics model, just learn the whole thing, but your physics simulation is also not accurate enough to just trust it 100% and ignore the data. I think, and I see this in all sorts of disciplines. If you're trying to fly an autonomous helicopter, you may have a physics simulator of the helicopter that's not great, and you have data on how the helicopter flies. If you're trying to control a robot arm, same thing. If you're trying to control a giant machinery, you have a physics simulator that's okay but not great, and you have data. I think that learning to figure out new paradigms, so we're going to simulate how cloth works, right? My friend Ron Fetko in computer science talks about this with physics simulators for cloth, they're okay, not great, and you have data for how a few pieces of cloth work. Can you merge these together? And I think climate modeling is maybe one of the most exciting ways to work on an important problem, but also push forward this exciting cutting edge area for computer science. In addition to climate modeling, other things I hope the AI community and Stanford community will step in to work on. Mitigation to reduce emissions, everything from better ways to move us toward renewable energy sources, to smart grid, to, and I think machine learning, AI, not panacea, but can play a huge role in improving these abilities for our ability to develop mitigation solutions. Or adaptation. Today there is already nascent work, some of which you hear about, and some of which is being done by various companies to predict or to detect and to take action to protect us from fires, floods. But I think many ways to get information to people or to governments will help us with adaptation. And finally, restoration, which includes things like replanting some of the forests that we've lost, and geoengineering. I don't think any of us really know if it's a good idea or not to spray seawater into the air in order to encourage cloud formation, in order to make the world more reflective so that we reflect more sunlight and the climate warms more slowly. Or maybe instead of spraying seawater, maybe spray sulfur into the atmosphere to change the albedo of the planet. I think these are exciting, sometimes very controversial possibilities, but our modeling abilities can play an important role to help citizens and governments answer these questions, as well as if some of these solutions turn out to be the right ones, then we may end up needing to deploy massive fleets of robots around the world at a scale that has rarely been seen before. And of course, those of us in AI robotics will have a huge role to play in building these solutions as well. And also, I still just like building robots, right? That's just fun. So I think there's a lot of work we can do, and we put this symposium together because we wanted to share some ideas with many of you and invite all of you in the Stanford community, if you wish, to learn about AI, learn about climate change, and maybe work on and play an important role in what may be one of the biggest problems facing humanity of our time. It turns out, of course, there is already exciting work done on campus on AI applied to climate change. And what you hear in the next hour is presentations from 6 different groups. Many of these had started life as a CS230 deep learning or a CS229 machine learning class project, or had intersected with those classes at some point. And what you hear from these different groups of students will be everything from prediction of fire risks to smart grid solutions to and on and on and on. Right? And so I think the format of this meeting is I'll invite the teams to come up to present. I'm going to ask you to hold questions until the end. I think after we wrap up, all the presenters will be around and you're welcome to ask them additional questions. But after hearing about these, I hope it will inspire some of you at campus, and I hope also the broader global AI community, even beyond Stanford, to consider working in some of these problems. And at the end of this session, at the end of the symposium, we'll also share some ideas for how you can get involved. So with that, I'll invite down the first speaker in a second, but let me just thank you all very much.
All right. Hi, everyone. First of all, thank you so much for inviting us here. We're really excited to be here. My name is Caroline Familietti, and this is Natan Holtzman. We are both first-year PhD students in the Earth System Science Department here, and today I'll be telling you a little bit about fire and machine learning. So fire is it's a real and growing problem for us here in Northern California, and because of this, we were both extremely interested in trying to see how we could use some of our learning algorithms to better understand its development based on preceding climate conditions and land surface conditions that would tell us something about what fire might occur. And so all of us here are seeing our fire regime changing in real time. It has been established that climate change impacts fire regimes, for instance, through shifting precipitation patterns. And in California, this means we're seeing increases in the magnitude, frequency, and duration of fires. And of course, along with this come associated increases in risks to human populations and to ecosystems. So it's extremely vital that we start to think about how to understand patterns of fire ignition and fire spread for the purposes of dynamic land and resource management. And we can start to try to do this by taking advantage of some of our learning algorithms alongside a vast data set of climate observations, land surface observations, to really begin to unpack complex variable interactions and think about how climate change comes into play here. So our objective was to think about what climate and land surface properties best predict fire occurrence. Now, we relied a lot on satellite remote sensing here, and it's quite important because it lets us attack our objectives in a unique way. It lets us look at land surface processes essentially over sufficiently long time scales. For instance, the MODIS instrument aboard the Terra satellite, which you can see here, provides wall-to-wall maps of relevant pre-disturbance conditions at a spatial resolution of 1 kilometer and a temporal resolution of 1 day. So you can see that this is a really extremely valuable and really robust wealth of data for us to use as the foundation of our learning algorithms. We created a data set that characterizes pre-disturbance conditions impacting the likelihood of fire, and we focused on the northern half of California, which is indicated here. We created a data set that was divided into two main categories, the first being climate variables, and the second, vegetation variables. So an example of a climate variable would be something like land surface temperature, which is mapped here. And an example of a vegetation variable would be something like the normalized difference vegetation index, or NDVI, which for us indicates vegetation greenness. And the majority of these variables, which you may be able to guess, were derived from satellite remote sensing, from MODIS actually. Now, for all of these, we computed 4 variations. And these were different lag periods, ranging from 1 day to 3 months prior to the day a fire started. And this is a really important distinction for us to make, because we really only want to characterize, at least for the purposes of this project, we only want to characterize pre-disturbance conditions impacting the likelihood of occurrence, as I've said, and we're not considering here conditions once a fire has already broken out. So we're essentially computing these because we don't know a priori over what timescales these variables matter in predicting fire. So we extract all of these lags at all pixels in our domains over the period 2001 to 2017, and this yielded a data set of almost 1 million pixel days and over 100 features. And then finally, we leveraged the MODIS presence of fire product, which provides binary fire, no fire labels at all pixels on all days in our domain, and that's what we used as our method of supervision.
We implemented 3 types of models, all of which go for a binary classification objective, fire or no fire. Logistic regression is a linear classifier, and then boosted trees and multilayer perceptrons, also known as neural networks, are both nonlinear classifiers. To reduce overfitting, we selected some of the data, like 1 year of the data, to use as a validation set. And we selected the number of trees for the tree ensemble and the architecture of the neural network based on performance on the validation set. For the neural network, we chose 2 hidden layers, the first with 10 neurons, the second with 2, and ReLU activation. And also, for the logistic regression, we were somewhat worried about overfitting if we used all the variables in the data set. So we tested an experiment with forward variable selection. To examine which types of information are best predictors of fire, we trained all the models on 3 sets of variables. Climate variables only, vegetation variables only, which is just remote sensing, and all the variables. All of our models did better than the baseline, which is just predicting no fire everywhere and at all times, which is an encouraging result. We found that within logistic regression, the forward stepwise feature selection actually hurt performance, which suggests that we're not overfitting even when we include all 100-some variables. Especially for the nonlinear types of modeling, the vegetation models were more accurate than the climate-based models. However, as expected, the models that include all sorts of data were the best. And we can visualize our predictions for our test period, which was the 2017 summer, on a map. And don't worry about the scale, showing that it's sort of arbitrary and scaled to the training data set. But what's important is that we actually predict much higher fire risk for the Central Valley than for other parts of Northern California. And we think that's due to an issue with our training data that we didn't anticipate, which is that the data labels anything that's burning as a fire, whether it's naturally occurring or human caused. And there happen to be a lot of fires that farmers set in their croplands intentionally. The model picked up on that and predicted a lot of fire in agricultural areas. So in the future, when we want to refine our model, we'd probably leave out croplands to focus only on wildland fires. In conclusion, we've shown that machine learning can be useful in predicting fire risk. and that both climate variables and remotely sensed vegetation characteristics are useful in this prediction. And these models can pretty much be directly applied to predicting fire risk in a future climate. We just can plug in future predictions of temperatures, wind speeds, precipitation, and get an estimate of the relative likelihood of fire 50 years from now, say, compared to now.
Thanks a lot.
Hi. I'm Thomas Navidi. I'm a third-year PhD student working with Professor Ram Rajagopal. My primary research interest is on smart grid solutions, particularly with controlling distributed energy resources. And so today I'm going to talk to you about the control of distributed energy resources without grid models using reinforcement learning. So to begin, I think we can all agree that renewable energy is part of the solution to climate change, and there's been a lot of progress recently on achieving that goal. For example, this plot here shows that the capacity of residential solar PV or photovoltaics have been increasing very rapidly in the past few years, and this is great for climate change due to the reduced emissions. However, it causes a lot of problems in the actual distribution networks, which I'll illustrate here. This is the infamous duck curve, as it's called in the energy industry, because the curve sort of resembles a duck. Basically, as you can see, the years go by and the solar capacity is increasing, such as in 2016, during the daylight hours around noon, the net load is much lower than what it used to be, and this is due to the solar penetration. And then as soon as the sun sets in the evening, we can see there's a very steep increase in the net demand. And these higher peaks and lower valleys create larger voltage fluctuations in the distribution network, and these can cause reliability problems. So the challenge is, how can we combat these issues brought about by solar? So people in the industry have been looking towards lithium-ion batteries. Recently, they've become more economically viable, as seen the price has decreased 5 times in the past couple of years. And the installation of distributed batteries can provide power balancing for the distribution network and profit for the owner due to energy arbitrage. And it can also help provide voltage management, which is the issue that I will discuss here. So we have 2 main goals with our batteries now distributed in this network. The first goal is energy arbitrage, which is defined as the profit you can make from buying electricity at a low price and then selling it later at a higher price. And this is done because the price of electricity is based on supply and demand, and therefore there's usually an elevated peak price in the evening. For example, this is what California residents may pay on their time of use electricity bills. The second goal of our storage units is now to reduce those voltage fluctuations I mentioned before. So we've defined a metric to define the lack of power quality in the network. Basically, it is just the sum of squared voltage deviations from an allowed band, as illustrated here. So we can combine both the arbitrage profit reward and this penalty for voltage deviations into a single function. And traditionally, we use some sort of optimization and some sort of scheduling to solve this problem. However, that assumes we have knowledge of all of the grid parameters, but in real life, the grid parameters are often unknown, even to the utility company who manages the grid. And so therefore, we approach the solution using reinforcement learning to find a strategy to control the storage units without the grid models. So the overall system consists of 2 components. There's a cyber system and a physical system. The cyber system is our reinforcement learning model, and here I've used this deep deterministic policy gradient. It consists of an actor network and a critic network. Then the physical system consists of the wholesale power market as well as the distribution grid itself, along with the homes in the grid and then the storage units within the homes. And then these 2 systems interact by sending the price information from the markets to our reinforcement learning model, as well as the power consumption of all of the users in the grid, all of the houses. Then the actor network can determine a storage schedule, which will be sent to the storage units. They will then execute that schedule, and we can measure the voltages across the grid. And that voltage information, along with the arbitrage price information, is sent to the critic network, which then informs the actor network how to better adjust its policy in order to be more optimal. So there's several challenges with this sort of layout. The first is the problem is too high dimensional to learn a good strategy from random exploration alone. Therefore, in order to tackle this, we initially trained a known heuristic strategy to the actor network, which basically just optimizes the arbitrage profit while ignoring voltages. Then what we do is we explore random perturbations onto this known heuristic policy. So here is just an example of 1 day of operation of the battery. As we can see, the blue line is the neural network, and around hour 8 we can see there's a big dip, whereas the heuristic misses that dip, and that corresponds to a voltage violation. And for the average data across a month of operation, we can see that the total performance, when you combine the arbitrage profit and the voltages, improves from -26 up to 20. However, there's still a lot of room to reach the true optimal solution, which is at 60. And so the future work is to discuss how to achieve better performance. First, we can help the convergence of the learning by incorporating trust region policy optimization, which is a well-known technique in the reinforcement learning community. And then furthermore, we can improve our exploration strategies. Rather than just random noise, we can check out some exploration based on the voltage we receive. And then in order for this to be really applicable in real life, it has to scale up to a large number of storage units. And that can be quite tricky considering reinforcement learning does not usually scale well with very high dimensions. And finally, this solution can be incorporated into a broader storage goal, which is part of my research with the PowerNet project at Stanford, to incorporate all sorts of aspects of the grid, such as ancillary services, and also minimizing costs using storage units and other devices such as air conditioners. Oh, thank you. That's all.
Hi, I'm Stephanie.
And I'm Michael.
We're both second-year grad students in the Air Astro department, and we're going to be talking about our project for machine learning that is about identifying lakes in the Arctic using satellite imagery. So the motivation for this project, as a lot of you know, the permafrost is melting. There's a lot of methane that's trapped under the permafrost right now, and as the ice melts due to rising atmospheric temperatures, the methane is released into the environment. And it's a much more potent greenhouse gas than carbon dioxide. It has about 30 times the effect. So you can imagine that the positive feedback cycle we're getting with all the CO2 happens with methane also. So we were looking at trying to just identify lakes that might be causing this problem. And that's the first step towards actually solving the problem. So the scenario, like I said, these methane reservoirs exist underneath lakes in the Arctic, and we can detect them because the methane bubbles up from the bottom of the lake, and that prevents it from freezing over in the shoulder season. So in early winter or late winter, when the rest of the lake will be frozen over, the location of the methane bubbles won't yet be frozen, which means that we can detect it from satellite imagery using either the visual spectrum or near-infrared spectrum. You can see in this image there's a frozen lake and there's a little spot where it's not quite frozen. Now in order to be able to find that spot, we have to first know where the lake is, and you can see in the wintertime everything is all snowy, so you can't really tell what's a lake and what's not a lake. So what we're doing is trying to identify where the lakes are in the summertime when you can see the difference, and then we'll have the location, and then we can go back and figure out which ones are emitting methane, and then that identification leads us to be able to solve the problem either by flaring or by capturing the methane in some way. So our goal for this project is just the very first step of that, which is finding and isolating these individual lakes using satellite images. There's not a lot of labeled data out there. There's no giant data set of lakes and their locations, so we were using a sequence of unsupervised clustering algorithms. The first step was to cluster based on the pixel color, so we can divide land from water. And then we cluster based on the pixel location, so we can isolate individual bodies of water. And then once we have our individual body of water, we want to know if it's a lake or a river, so we use an EM algorithm for that. So the first step, like I said, is k-means. So we consider this region from Planet Labs satellite data. So that's something I forgot to mention. Planet Labs has a whole fleet of satellites, so we have it's updated very frequently, and so we have a lot of satellite data to work with. So this is a new area that we can really take advantage of. So this is an image from Planet Labs. Like I said, we're looking at the summertime where the land and water is very distinct. And so we can use k-means just purely based on the pixel color to separate out all of the pixels that are water versus all of the pixels that are land.
So after k-means, as Stephanie pointed out, we are left with pixels that are water and pixels that are land. And this is great, but we don't really know pretty much any location data about the pixels. So we don't know which pixels correspond to rivers, which pixels correspond to lakes. So we do a density-based clustering algorithm called dbScan. And what dbScan will output to us is an isolated body of water. So either a river, a lake, or a combination of rivers and lakes. And this is great. It's an important step, but eventually we're going to want to isolate single lakes by themselves and also get rid of rivers. So the issue with rivers is that they don't freeze over as quickly in the shoulder seasons, and so they can pretty much lead to us getting false positives because we'll look at it, say it's not frozen, and it could be methane, but it's actually not. So once we have these isolated river or just body systems, we put these clusters into an expectation maximization algorithm. So the goal of this is to decide whether or not this body of water is a river or a lake or a combination of the two. And the way we do this is we fit just pretty much Gaussian, multivariate Gaussians to the locations of the pixels again. And the thought behind this is that when we fit it to a lake, for example on the right, the fitted Gaussian will be nice and a little bit more circular versus a river where it's going to be really, really narrow. And then we can look at the covariance matrix of the fitted Gaussian and kind of just put a cutoff on that based on the shape. And we can decide whether it's a lake or river based on that. The issue is though, well not an issue, one problem we had to solve is when lakes and rivers are connected to each other. So say we have a lake right here and a river right here. Ideally, we'd want to fit a Gaussian to the lake and then a separate Gaussian to the river. And so we needed to decide how many Gaussians to fit to each set of water pixels that come out of dbScan. And to do that, we ended up just running EM multiple times on each body of water. And then we'd look at which, how many Gaussians fit the data the best. And then we'd throw a regularization term. The equation kind of covered up some of the notes, sorry about that. But we throw it on a regularization term to pretty much prevent overfitting so we don't fit an entirely new Gaussian to one tiny little shoot off of a lake or something like that. And then pretty much with this essential kind of like a loss function, we can choose the right number of Gaussians to fit to each body of water. And then pretty much after this, we're done. We can filter out through every Gaussian that we fit and decide whether that's a lake or a river based on the shape. And then we can go forward using those pixels. We compared this to a much simpler method, which is just a bounding box. We take the body of water, lake or river, draw a bounding box around it, and then compare the number of water pixels in that bounding box to the total area of the bounding box. We found this method was great. It was easy to implement, but we found it was a little bit too simple. Again, if a lake is connected to a river, it would classify it as a river, as most of the bounding box area will be taken up by the river. So the best results actually came from using the EM algorithm. So our results are mainly that we are able to identify a lot of lakes in an unsupervised fashion. So this is obviously a bit qualitative because Stephanie and I are not explicit experts on what's a lake and what's not. But as you can see, we're able to take this picture and essentially find the lakes and eliminate the rivers. And so to I guess, summarize the overall process, we start with a picture during the summer of lakes and rivers. We can now isolate the lakes, and we know the position of the lakes. And then now, when winter comes, we can take a picture from the same location and look at just the lake regions of that picture, which is really powerful. So future work, a lot of these data sets that are coming from Planet, as Stephanie said, include the near-infrared spectrum as well as the visual spectrum in their data. And this potentially allows more ways to separate land from water. There's some methods using the near-infrared that would essentially replace the k-means part of our algorithm. And then from here, because we know we can identify lakes, we need to start identifying where the methane is coming. So we just start looking at pictures across the Arctic and hopefully find some methane dispersion that we can therefore, go out and hopefully solve. And that's it. Thank you.
Okay, so as Professor Ng said, I experimented with using CNNs to improve climate ensembles. As a bit of background, my name is Brian Reed, and I am a second-year student in management science and engineering. I've been working with Professor John Wyant on sort of climate model diagnostics, in particular moving towards shorter term and regional forecasts. So this is an area of active research on the climate science side of things. It's a time frame from a couple of years up to a decade or two that is really of interest to decision makers. So either decision makers in climate services, so people in insurance or financial markets, or people on the trying to mitigate climate impacts, trying to adapt and see how the storms are going to change, temperatures are going to change, things like that. One of the challenges for this is that it's sort of right in the middle, right in the sweet spot where we haven't really developed a lot of the models yet. There's an active model comparison project that's going into this region right now. But it's difficult. So on the time scale, weather models tend to be accurate over a couple of hours, maybe a couple of days, and then the accuracy degrades as you get time, as you extend that time frame. And on the other side, climate models tend to be good over scales of decades to centuries when the forcing from greenhouse gases overwhelms any of this natural variability. So on the spatial side, climate models are also better at higher levels of aggregation. This has been an active area of research in the climate modeling community, some of it just driven by advances in computing power. So as computers get better, you can resolve these models at finer and finer resolution and start to include more physical processes in them. So the goal here, as Professor Ng hinted at in his introduction, there's some really interesting work to be done sort of trying to emulate the physics in these deep learning projects. I took an opposite tact and I said, so we have right now 40 different modeling centers, 40 plus modeling centers who are developing these climate models. They develop these ensembles that have a spread of different predictions. And then right now, so there's some Bayesian techniques, and then they tend to sort of just be averaged together. And then you'll see a climate ensemble average as the model prediction. So I was kind of interested in seeing if you could use these existing climate models, which tend to be run for longer time horizons, and use a CNN to revise that weighting process so you improve resolution over smaller spatial scales and shorter time scales. So in terms of what that looks like, the ground truth data was observational data from Berkeley Earth. So these are weather station and reanalyses over the last 100 plus years. The input data is actually climate model output. So you see here different ensemble, different forecasts from different models. They're hindcast back into the past. These would extend hundreds of years back. And then they're run into the future. There's a note about it, the graph there. So each of those represents a separate model. So the time scale that we're looking at, again, I start in 1900 and I go to 2005, and we do 1900 to 2000 as our training and dev set with a 90-10 split, and then simulated out-of-sample prediction set from 2000 to 2005, not using any of the data that we've trained on. So in terms of the data processing, this takes a little bit of work to fit into the model. So we choose 3 of the models from, this is the Earth Systems Grid Federation's Climate Modeling Intercomparison Project. Basically, it's a big data repository with all of the model outputs online. So we choose 3 of these lines. That's not actually representative. I don't map them, but say we choose 3 of them. And then we plot this model output over this region of North America that you see here. So we take the model output from one model projected on 2-dimensional space, and then we do this for 3 models and stack it. So you've probably seen something like this for a red, green, and blue image. Here, it's just going to be climate model values in each pixel for 3 models stacked. So this is a preliminary approach. I kind of was just running this for proof of concept and to see if there's some traction. So the initial model was just using these model outputs from one day, so for every day from 1900 through 2000. And then alternative architectures would involve just stacking model outputs from different days. So instead of doing like a weighted average of pixel values over time, you could just stack the model output itself. So I ran it over 1 day and 5 days. If you were actually going to try to implement this, you would do longer time horizons. But again, this is sort of just a proof of concept. The actual model, so this is a simplified representation. I used a UNet architecture. The advantage of this architecture is that you put in an image and you get out an image. So we can put in these two stacks of images and then get out a prediction in the end. So the CNN will go through each of these stacks and create locally weighted model outputs through this convolution-deconvolution framework. Again, this is a pretty simple approach. We just did 2 layers of this, but if you wanted to, you could go crazy with as many layers and different tuning parameters as you'd like. And then, oops, got ahead of myself. So here I just used normalized max temperature. So the values that you see there are just a normalization of daily max temperature over this region. And yeah, so we train it using mean squared error loss, and then this visualization, so it's trained using mean squared error loss, and then I was just looking for systemic biases, so instead of squaring it and losing the sign, I just sum up all of the pixel values for January 1st, 2001 to December 31st, 2005, and basically the darker values, darker red, darker blue, represent higher modeling error. One thing to note, another caveat here, the oceans are picked up in the ensemble averages because these are over land, so you can kind of just mentally discard the predictions over the ocean, but if you focus on the prediction over land, you get a better one-to-one mapping of ensemble average to UNet. And basically the fact that the UNet models are washed out means that these are more accurate predictions. So I'm going to present one figure with the caveat that this doesn't account for the ocean error. So not accounting for the ocean error, there's a significant improvement with the CNN because it kind of learns what is the ocean and it cancels that out. So you'd expect to see a more muted improvement, but still a pretty strong improvement if you accounted for that and compared the UNet to this straight ensemble over the modeling averages. So in terms of next steps, again, this was a pretty preliminary implementation, but it's kind of a new stab at taking a new stab at weighting across models. Some things that you could do if you were to continue in this path are to relax time stationarity. So right now there's one filter over the entire time period. You could change that, obviously adjusting the oceans. And then there's some interesting work being done on sort of pure machine learning approaches. So in particular, over the last 30 years, as some of our earlier presentations have hinted at, we have awesome satellite data records. So you can sort of reconstruct with a high degree of fidelity the climatology over these time periods. And people are starting to go in a direction of physics-informed AI and starting to learn eddy flows and circulation and things like that just based on data itself. So, thanks.
Hello, everyone. My name is Wael Abid, and I am a sophomore in computer science. And today I'm going to be presenting about load and solar power forecasting in a residential setting. This work has been done as part of my work on the PowerNet project with Professor Ram Rajagopa, and as a final project for CS230. So an electrical grid is the main factors that affect an electrical grid are generation, delivery, and demand. What generation is just that the power plants, whether they're coal-fired or based on renewable energies or any other fuel, delivery is just that the transmission and distribution lines that connect the power plants and the customers. And the demand is just the demand created by the customer, whether it's an individual, household, or a farm, or a factory. And just to give you a small outline of how the thing works, I will try to focus on how things work. So that after the electricity is generated by the power plant, it's the voltage is stepped up and is transmitted to through very long distances, and sometimes crossing international borders, until it reaches what we call wholesale customers, which are basically the companies that distribute the electricity to people. And these companies distribute this energy until it reaches to different substations, until it reaches these substations, and at that level, voltage is stepped down, then moved to other substations where the voltage is stepped down as well, depending on where the electricity is distributed, whether the place is residential or agricultural or industrial. So physically, electrical power is created by generators to meet demand via delivery hardware. But practically, it's the demand, one of these three factors, it's the demand that drives the other two factors. So climate change affects all of us and affects all of our lives. So it's normal for it to affect our demand. And one consequence of climate change is more extreme weather. And depending on where you are in the world, you can notice it as decreased air temperatures, precipitations, sea level rise, or more frequent and severe events like fires, typhoons, floods, and these factors lead to a huge strain on the electric grid, and it could, at some time, it could render it very unreliable. And we all know how a reliable electric grid is central to any urban development and to every service provided in a modern city, from healthcare to finance, commerce, transportation systems, you name it, there's a lot. And electrical power, just like any commodity, is traded, so its price can either go up or can go down. And climate change, since it affects demand, it's going to affect the economy, and it's going to affect, by consequence, the way we exploit these natural resources. And let's take, for example, one case where you live in a city or some region where you have, in 50 years, you have very hot summers and very cold winters. What's going to happen is that your demand of energy is going to increase both in the winter and the summer, because you're going to need more heating in the winter, and you're going to need more cooling in the summer. And at this point, who knows how the markets where electric power is traded, how are they going to react? And also, who knows how, at which point, with all of this strain put on the power grid, at which point it's going to break. Another important factor to consider with the prices of solar panels dropping every year, and with people getting more and more aware of this climate change problem, people are installing electric panels on their roofs, but this great form of energy is not as easily controlled as the other, or predictable as the other sources of energy, which doesn't make it any less great. but this also poses another question, and it puts us in front of another challenge, because now people are able to produce their own energy, and at some point they're going to be able to surpass their needs, and that surplus, they're going to be able to sell it and put it back to the grid. However, our grids are, when they were designed, at least the old grids, they were not designed to accept the other inflow. They were like central, and these people are just accepting electricity. And this, of course, is going to affect the markets where electricity is traded as well. So, faced with all these factors, we have so many factors, so much information that we need to find where we need to find the compromise. And here, artificial intelligence and forecasting becomes an urgent necessity. So what electricity forecasting is about, if you remember the three factors, generation, delivery, and demand, and demand drives the other two factors. It's about demand forecasting, price forecasting, and the forecasting of electricity from the renewables. And why it's important is because if you're a power plant, for example, and you're generating some energy for those different wholesale customers that they're going to distribute to customers, you're going to need to know how much fuel you're going to burn, or how much coal you're going to burn. And if you're a company that distributes your electricity to people, you're going to need to do maintenance. You're going to need to know if you need to expand on your hardware, and also financial planning. So what we did is a machine learning model. It's an LSTM, but we tried a lot of things. So our data is basically a month of data. We were lucky to get it from PG&E, even though it's really difficult to get power data, especially that they're sometimes private. It's 30 days sampled at a 1 minute rate, and over 95 houses. And we had to downsample, otherwise it would be very variable. So we get this figure. And we started with a baseline of the seasonal ARIMA model, which gave a decent result. But we tried to improve on the existing models and reach state of the art, which we were able to do with both the LSTM model, LSTM encoder decoder model, and the convolutional LSTM. But we chose the LSTM model because it took shorter to train, and it had much less parameters. So these results are state-of-the-art: 364 kilowatt hours root mean squared error, and 11.29% of normalized root mean squared error. Future work, it's all about the data. We need to incorporate more factors. More weather factors are important since they affect demand. So humidity, precipitation, and wind speed, and like data on a longer span of time, as well as experiment with more models, new sophisticated models, just like the transformer model. Thank you very much.
Hi everyone, I'm Jose Bolarinos. I am a PhD student, fourth year in environmental engineering, co-advised by Anusha Jami and Ram Rajagopal.
Yeah, and I'm Chris Pierce. I'm an STPD student and a candidate for the Computer Science Master's Program.
And I'm going to use I suppose, let's see, how does this work? I've never used one of these things. Oh, nice, okay. Yeah, so we're going to talk to you today about using deep learning techniques to monitor the operational performance of an anaerobic wastewater treatment plant. And why is this related to climate change? So why anaerobic treatment? So as Professor Eng said, anaerobic treatment is a new and improved technology relative to conventional treatment methods that are currently really widespread and used mostly. Conventional methods are very energy intensive. They consume 2 to 3% of the electricity in the US just to treat your wastewater. Anaerobic treatment methods are much more energy efficient because they don't require oxygen to drive the process. So you don't need to put all this energy into aerating your reactors, the water in your reactors. Perhaps more importantly though, the chemical energy in waste with conventional treatment methods is just released into the atmosphere as CO2 and is not recovered. But with anaerobic treatment, you can hack that biological process by using anaerobic organisms that can recover the energy from the chemical energy in organics and wastewater as methane, right? And that provides a carbon neutral source of energy, which is pretty substantial. So in the state of California, if we were to harvest all of the methane from our wastewater, we could essentially supply all of the peaker power plants that provide grid flexibility in the short term, 80 to 90%. So what's the problem here? Well, this is a great new technology, but it's very finicky and very delicate, and in particular, it's very sensitive to pH, which has to be right around 7 for it to work. And so for this to be scalable and available and widespread, we need a way to efficiently monitor pH. And so the purpose of this, of our work, is to use deep learning to, first of all, predict pH in anaerobic reactors 1 to 24 hours ahead. So it's just a forecasting exercise. And identify and anticipate and prevent operational issues. And then 2, to make this process self-regulating in a sense. So to use what we learn from the forecasting models to create a model that can tell us when a pH probe needs to be recalibrated. Why are we using deep learning methods? Because these sensors are really finicky, and they can have weird jumps and mechanical issues that will make traditional time series forecasting methods not work as well as deep learning, which can handle this sort of stuff more flexibly. So we trained our models using data from the Kotiga Center, which is a pilot scale wastewater treatment plant that was launched on the Stanford campus a couple years ago. Incidentally, it's anaerobic. And we tested 3 different deep learning approaches: convolutional neural networks, recurrent neural networks, and attention-based models. And these were benchmarks against standard ARIMA, or autoregressive moving average-based time series models, and then a state-of-the-art Bayesian time series model, which is the Facebook Prophet, which was published a couple years ago. And with these, we achieved an optimal best mean squared error performance, about 0.5, relative to a pH of 7, which is not bad, but hopefully we could improve on it.
Cool, thanks. So, look, of the models that we tried, the one that we found to be most successful was the recurrent neural network structure. We tried a range of these kinds of problems. First of all, looking at encoder-only based models. So, knowing that we have a 24-hour period in the data, we took stacks of 24-hour blocks of data, fed them into a gated recurrent unit, and did the predictions straight off the top of that. So, unidirectional and bidirectional gated recurrent units for that particular model. We then moved to an encoder and decoder stack. So for anybody that's worked in language translation, this is a very common model that's been used here, and we were interested to see how this performed in a time series forecasting environment. So feeding the results from the encoder stack out into the decoder stack to produce the forecasts there as well. We then additionally started to work with teacher forcing based methods, so taking the forecasts from each time step and feeding them back directly as inputs into the model, and finally using a multi-stack RNN model as well to look at how we could parameterize the whole thing. So bearing in mind that the Facebook state-of-the-art model was able to get down to an error of 0.5, the very best model that we were able to train here cut that down to an error of nearly 1% of that, so 0.003. The critical problem, as Jose said, that we were trying to deal with here is that you have some really big structural breaks that happen in your data, and what we've shown here is that these kinds of models are actually able to address one of these really big problems that you often face in time series forecasting. Moving from that, we've then actually taken the work forward a bit, and one of the things that we've done is we said, well, attention mechanisms are a very interesting feature that have come out of some of the more recent neural network modeling. And so what would happen if we actually kept the attention mechanism and dumped the neural net part itself? So we just had an attention-only model. And what we have built here is a model that uses the variance between different channels of the input as an attention feature. We can run this one with as few as 3 trainable parameters inside the model, but retaining the entire attention mechanism in there. And you can see best performing model here again cuts us down to a root squared error of 0.003 versus some of these top performing Bayesian models that are getting a result of 0.5 on that. So the attention mechanisms just by themselves have actually got some very interesting applications in this area. We're moving the models on now to start looking at some more categorical predictions, because you've got the opportunity to do this with discrete data, but with continuous data sets. But if you bin it into categories, then you can actually start to look at non-Gaussian transitions, where you might have like quite large movements between data points that you want your model to be able to capture. And so we're exploring using both the WaveNet and transformer-based models to look at some of these where we can actually start to capture some of these more complicated relationships that we're seeing inside the models as well.
Yeah, so with this forecasting approach, ultimately the next step will be to use laboratory data, which is plotted here. You have on the x-axis the sensor value, on the y-axis the laboratory validated measurement of laboratory pH. And so that will be our data source to build on this model and use a transfer learning approach to anticipate the need for when a pH probe needs to be recalibrated. And this approach can be extended to other critical processes that are going on at the Codiga Center to make anaerobic wastewater treatment better, in particular, for example, managing membranes.
Yeah, and I mean, one of the reasons that I'm particularly interested in this is that we see this as sort of quite a big part of the Industry 2.0 approach. If you're going to be building models of how entire factories work, then I guess I see 2 key components that you need to do this. One, you need universal forecasting models that can actually capture these kind of complicated interactions. And as Professor Ng was describing, that may be a combination of deep learning models as well as basic knowledge of physics. And then combining that with optimizing models as well, so reinforcement learning approaches, for example, to do that. And if we're going to actually get on top of problems like climate change, we really need to be able to find much more efficient ways to run our factories and run systems like this. And we see these kinds of approaches as being core to actually being able to get universal forecasting systems together that can help to power these Industry 2.0 type systems. So I'd like to say thank you very much to Professor Ng for sponsoring the symposium, and also to Jeremy and Sharon for organising the whole thing. It's a fantastic initiative.
So let's see, we've come to the end of the technical presentations for today. Just a couple last thoughts. We had asked all the presentations you saw in the last hour were student-led presentations, and we wanted to have this symposium with student presentations because I wanted all of you to have a vision that maybe if you work on this, I would love if in 6 months or a year, one of you, is the one invited up on stage to present your work on AI for climate change, maybe on campus, maybe an academic conference. I think in climate change of all disciplines, I think that starting with the academic research, starting with the papers, the presentations, that's a great first step. For myself, I don't count my work as done until I count my work as done not just when we publish a paper, but when we actually have an impact. And that's one of the orientations that my PhD students and I, that my research group and I have often had in a lot of our work, that our job isn't done when we just publish a paper. Our job is done only when we have a concrete impact. Now, just a couple more slides and then we'll wrap up. I hope that many of you will get involved. And with the rise of many disciplines, is not that a small group will write one paper and do one project and then we're done, right? Climate change is a large problem, it's multifaceted, there are many different projects and many different problems that work on. They'll take many professors, many students to do good work to make a difference. If you want to get involved, one of the ways to do so, out of many possible ways to do so, is that my group is holding a AI for Climate Change bootcamp for the very first time this quarter. Some of you will know that my group has been holding boot camps for quite a while now on other topics, and we're launching our first one on climate change this quarter because we want to work with Stanford students to do more work in this space. We're fortunate for this first bootcamp to be collaborating with Professors Rob Jackson, Ram Rajgopal, and Sarah Knox. And you heard some of the names multiple times already in this presentation, since many of the presentations were with students that are already working with some of these professors. Professor Rob Jackson is the chair of the Global Climate Project, and we're fortunate to be able to work with him on his data set, on his unique data set, collected from a global network of methane emissions data. And so we studying that data and modeling that with him. Professor Ram Rajgopal is he's the director of the Stanford Sustainable Systems Lab, and he is also very well known for his work on Deep Solar, which is a database of solar panels across the United States, created using deep learning. So we're working with him on as well. And Professor Sarah Knox is a professor of geography and is expert in climate variability, land use change, and modeling of biosphere, atmosphere, exchange of water, energy, and trace gases. So there'll be multiple projects that we look forward to collaborating with them on, as well as at the bottom are the pictures of some of the CS as well as some of the climate students and postdocs. So if any of you are interested, please very warmly invited to apply with an application deadline in 2 days. And two of the student leaders running these boot camps are Jeremy and Sharon. I'll let them tell you a little bit more about this as well.
Pleasure, Jeremy. Thank you so much, Andrew. We're really excited to announce this boot camp. If you're interested in these projects that you saw before and are willing and want to dedicate 2 quarters to it, please apply. You'll be working in teams of students at the intersection of AI and climate change research.
Yeah, and the bootcamp is a fantastic way to get involved in AI research. Actually, 4 previous bootcamp students were accepted into CS PhD programs this past application cycle. So if you're interested in getting into research, the bootcamp is a great way to do that. But beyond all the work that we do in the bootcamp, we like to have a lot of fun as well. We do things like movies, picnics, and if we're feeling athletic, some sports and yoga and things like that. So we have a lot of fun.
Maybe only once or twice. So if you're interested in applying, please go to our website for the application. Again, the deadline is this Wednesday. It's pretty quick, and there is an interview. For those of you who do not have that much AI background right now, we will be hosting this bootcamp again in the fall and all future academic quarters.
Thank you.
Thank you.
All right. So with that, just to wrap up, thank you. Just to wrap up, thank you. Want to thank all the presenters again for the great presentations. There are only so many moments in history where you're invited to step up and do important work. This could be one of them. And certainly for myself, my students and collaborators, we're excited about the impact that the Stanford community, also the Stanford machine learning community, but also, frankly, the global AI community can make on one of the most important problems of our time. So I hope that some of you will be inspired by this to do some work in this yourself. So thank you all very much.